Quantum gates and quantum circuits are the basic building blocks of quantum computing. They are the tools that allow quantum computers to process information in ways that are fundamentally different from classical computers. In this video, we will explain quantum gates and circuits in clear, simple terms, focusing on ideas rather than mathematics, so you can understand how quantum computation actually works. To understand quantum gates, it helps to first think about how classical computers work. A classical computer uses bits, which can be in one of two states, 0 or 1. Classical logic gates, such as AND, OR, and NOT, take bits as input and produce a definite output. These gates are combined into circuits that perform calculations step by step in a predictable way. Quantum computers also use gates and circuits, but instead of bits, they use qubits. A qubit is not limited to being 0 or 1. It can exist in a combination of both states at the same time, a property known as superposition. Because of this, quantum gates do not simply flip values from 0 to 1. Instead, they transform the probabilities and relationships between states. A quantum gate is an operation that changes the state of a qubit or a group of qubits in a precise and controlled way. Unlike classical gates, quantum gates are reversible. This means that no information is lost when a quantum gate is applied. Reversibility is a key requirement in quantum computing because it preserves the delicate quantum information stored in qubits. One of the simplest quantum gates is the quantum NOT gate, also called the poly-X gate. It flips the state of a qubit, turning 0 into 1 and 1 into 0. But if the qubit is in a superposition, the gate flips both parts of the superposition at the same time. This already shows how quantum gates operate on multiple possibilities simultaneously. Another important gate is the Hadamard gate. This gate takes a qubit in a definite state and places it into an equal superposition of 0 and 1. After applying a Hadamard gate, the qubit is no longer in a single state, but in a balanced combination of both. This gate is essential because it creates the parallelism that gives quantum computing its power. Quantum gates can also act on more than one qubit at a time. These are called multi-qubit gates, and they are responsible for creating entanglement. A common example is the controlled NOT gate, or CNOT gate. This gate links two qubits in such a way that the state of one qubit determines whether the other qubit is flipped. When used with superposition, the CNOT gate can entangle qubits, creating strong correlations that have no classical equivalent. Entangled qubits cannot be described independently. The state of one qubit is directly related to the state of another, even if they are physically separated. Quantum gates are the tools that create, manipulate, and exploit this entanglement within quantum circuits. A quantum circuit is a sequence of quantum gates applied to qubits in a specific order. Just like a classical circuit diagram shows wires and logic gates, a quantum circuit diagram shows qubits as lines and gates as symbols placed along those lines. The circuit represents how the quantum state evolves over time. At the beginning of a quantum circuit, qubits are usually prepared in a simple, known state, often 0. Gates are then applied to create superposition, entanglement, and interference. The goal of the circuit is to shape the probability distribution of outcomes so that the correct answer becomes more likely than incorrect ones. One of the most important ideas in quantum circuits is interference. Just as waves can reinforce or cancel each other, quantum states can interfere. Quantum gates are designed so that unwanted outcomes cancel out, while desired outcomes are reinforced. This is how quantum algorithms achieve their speed-up over classical algorithms. Measurement comes at the end of the quantum circuit. When qubits are measured, their quantum states collapse into definite classical values, 0 or 1. The result of the computation is obtained from these measurements. Because quantum outcomes are probabilistic, the same circuit is often run many times to build up reliable statistics. Quantum gates must be applied with extreme precision. Qubits are very sensitive to noise, temperature, and interactions with their environment. Even small errors can destroy superposition and entanglement. This is why real quantum computers use error correction techniques and carefully controlled environments to protect quantum information. Despite these challenges, quantum gates and circuits are already being used in experimental quantum processors. Companies and research labs around the world are building increasingly complex circuits with dozens or hundreds of qubits, testing algorithms for chemistry, optimization, cryptography, and materials science. In simple terms, quantum gates are the actions that change qubit states, and quantum circuits are the structured sequences of those actions. Together, they form the language of quantum computation. They allow quantum computers to explore many possibilities at once and use interference to guide results toward useful answers. Understanding quantum gates and circuits gives you insight into how quantum computers think. They do not work by trying every answer one by one, but by shaping probabilities through carefully designed transformations. This makes quantum computing not just faster for certain tasks, but fundamentally different from classical computing. As quantum technology continues to develop, quantum gates and circuits will remain at the core of this new computational paradigm. They represent a new way of processing information. One that reflects the deep and surprising rules of the quantum world.